All right, so next up in the series of lectures on radiation is a fairly complicated topic. So now we're going to add in absorbing media and or reflecting media. So basically what we did before, we had two objects. Basically, we assumed there was nothing between them, there was only a vacuum. Now we're going to deal with what happens when that thing between them actually matters. So as I mentioned in previous discussion, relied on the fact that none of the energy was absorbed between the two objects of interest. So there's nothing between them, basically assumed it was a vacuum. In normal cases, when it's not a vacuum, normally some radiation will be either absorbed or reflected or other things happening to it. So we're going to start off by assuming that now the stuff between the two objects can now absorb radiation on its own and also re-emit that radiation by itself. So again, generally on Earth, we're going to have air between the two objects. Air being a gas, gases generally don't absorb too much, but sometimes that may be important. When you get to something like glass or water between two objects, those might be even more important. So this would be applicable to those scenarios. So starting off with dealing with just absorbing, so not going to deal with reflection yet. So absorbing transmitting systems. So basically I have my two objects, object number one and object number two, and some now new medium between the two. So technically this was here before, I just ignored it. Now I'm not going to ignore this medium. So I have this medium M, which can absorb and re-emit radiation as well as transmit radiation. So whatever comes off object one, some of it will transmit straight to object two, some of it will be absorbed into the medium, and then that medium will re-emit that energy, some of it back towards one, some of it over to object two. This is the simplest scenario for this. Again, I have two objects and some medium between them. For the medium itself, it has some absorptivity alpha and some transmissivity tau. Because I'm dealing with no reflection, that's the only things that can happen. Any energy hitting it is either going to be absorbed or transmitted. So those two added together adds up to one. Then emissivity, absorptivity, always the same value. So I can also write this as emissivity plus transmissivity equals 1. So just like we did before, I have some energy that's going to leave surface 1 and arrive at surface 2. That's going to be J1. That's all my energy leaving object 1. To actually make it to object 2, I need this view factor, A1F12. So that's now the fraction of that energy J1 that hits object 2. And then I only need the part that gets transmitted, because some of this energy is going to actually be absorbed into the medium. The rest of it's going to be transmitted. So the transmitted part is actually going to get to surface 2. So this is my total energy leaving surface 1, getting to surface 2. I do the same thing backwards. So leaving surface 2 and arriving at surface 1, I have J2, A2, F21 times the transmissivity. And then A1, F12, same as A2, F21 from my geometry view factor considerations. So I can do the net energy transmitted, take this A1, F12 times tau out of both of those terms, then one minus the other is the net energy going back and forth. So A1, F12 tau M times J1 minus J2. And then again, normally I want to write that as some energy difference, J1 minus J2, over some resistance type value. So resistance value, I have 1 over this whole thing, A1 F12 times tau, but tau is 1 minus epsilon. So 1 over A1 F12, 1 minus epsilon is that energy being transmitted. And then I want to look at what happens to the medium. So energy exchange between surface 1 and the medium. So I'm going to have some energy leaving the medium, and that energy Jm is epsilon m times EBm. So EB for the medium, sigma times t to the 4th for the medium itself, times its emissivity. That is the total energy leaving that surface. And then the amount of energy reaching surface 1, I have area of the medium, Fm1. So F from the medium to object 1 times this energy leaving the medium. And then again, that guy is just epsilon times EBm. And then once that energy hits object 1, that energy now needs to be absorbed. And so to be absorbed, scratch that, going the other way, starting off at surface 1 and then coming in to the medium, the amount leaving surface 1, I have J1. I need the amount going into the medium, A1F1M, and then the amount actually absorbed by the medium, alpha M, and then alpha is the same as epsilon. So the amount that leaves surface 1 goes into the medium is J1 A1 F1M times epsilon M. So I basically now have energy from the medium getting into surface 1, energy from surface 1 going into the medium. And so net energy exchange, again, I can take out AM FM1 times epsilon M, because those would be the same for both of them. AI Fij equals AJ Ji. So this is just the energy from the medium going into surface 1, energy from surface 1 going into the medium. Again, all this stuff is basically the same other than EBM and J1. So I have EBM minus J1 on top. Then the rest of this, A1 F1M epsilon M, I want as a resistance on the bottom in reciprocal form. Again, as mentioned before, if my medium is at some fixed temperature, then EBM is just sigma times the temperature to the 4th power, of course in Kelvin. And so now it's basically the same as what we did before. I want to find all my J values for all the surfaces. So generally I have 3 objects. So I'm going to have that triangular radiation network. So 3 J values, J for object 1, J for object 2, and a J value for the medium. And then of course my full radiation network depends on what else is going on, whether some of these objects are infinite, whether some of the objects are insulated. So again, general procedure, I want to solve for all my J's. Then from there I can find all my heat transfers. So example of this, I have 2 long concentric cylinders. First one has a temperature of 900 Kelvin, an emissivity of 0.4, diameter of 5 centimeters, that's the inside cylinder. Outside cylinder has temperature of 400 kelvins, emissivity of 0.6, and diameter of 10 centimeters. There's a gas between them, has some epsilon value for the gas of 0.15. I want to calculate the heat transfer rate between the 2 cylinders, and then I also want to find the gas temperature. So in terms of my radiation network, I have cylinder 1, I have cylinder 2, and then I have EB for the gas. And so my gas is kind of like a really big object. It's completely between everything. So I don't need a line here. Actually, better explanation of that is that my, never mind, yeah, EB for the gas is a really big object, so I don't have a line here. So for my resistances, EB for object 1, I need to make it off the surface. To make it off the surface, I have this emissivity resistance, 1 minus epsilon 1 over epsilon 1 A1. Same thing for object 2. I have this 1 minus epsilon 2 over epsilon 2 A2. And then between 1 and 2, I have this view factor resistance, 1 over A1 F12, 1 minus epsilon for the gas. So again, that's going completely straight from object 1 to object 2, transmitted straight through the gas. So this 1 minus epsilon, again, is transmissivity. That's the amount of energy that goes straight through the gas. The other way to get to object 2 from object 1 is to go through the gas. In other words, once I'm off surface 1, I get absorbed into the gas. That absorption resistance, 1 over A1 epsilon G F1G. And then you have to get re-emitted from that gas. To be re-emitted, that's 1 over A2 epsilon G F2G. And then that brings me to EV2. So again, 2 ways to go there, from 1 to 2, either straight through, transmitted through the gas, or absorbed and re-emitted from the gas. So calculating all these resistances, these 5 values here, 1 minus epsilon 1 over epsilon 1 A1. Area 1 is just pi times D1, that's my inner surface. So around the inside surface of the cylinder itself is pi times D. Technically, there's also a length in there. So pi times D goes around the cylinder. I should technically multiply that by the entire length of the cylinder. but I'm assuming that these are all per unit length, so I'm not going to worry about that length. So area is just pi times d. Then plugging all those values in. For object 1, the inner cylinder, I have a resistance of 9.55. Same thing for the outer cylinder. Slightly different numbers for epsilon and d. Gives me a resistance of 2.12. Then I need all my shape factors. So 1 over A1 epsilon g, F1g. So this is going between the first object and my gas. Again, the area here for area 1 is pi times d1. Epsilon for my gas is 0.15. F1 to the gas, if I'm looking out from the inner cylinder to the outside, I basically have to hit the gas. So view factor there is 1. There's no way I can make it to object 2 without going through the gas. So F1g is 1 in this case. Gives me a total resistance of 42.4. Similarly for surface 2, my outer cylinder, 1 over A2 epsilon gas, F2 gas. Area pi times d, epsilon 0.15. Again, view factor. If I'm coming off the outer cylinder towards the inside, I have to go through the gas. So my shape factor again is 1 in that case. Then lastly, resistance from between the two cylinders. 1 over A1 F12, 1 minus epsilon gas. So 1 over pi times d1, that's area 1. F12, again, is 1. There's no way, if I'm coming off object 1, there's no way to not hit the outer cylinder. Because I'm assuming it's really long, so I'm not going out the end. So again, F12 is technically approximately 1. I'm calling that 1. Then 1 minus epsilon gas. So 1 minus 0.15 gives me the transmissivity. Resistance in that case, 7.49. So now I have the values for all these. So 9.55 here, 2.12 over there, 7.49 here, 42.4 here, and 21.2 down there. Now I can find my overall resistance. So there's two ways I can get from object 1 to object 2 for my overall resistance. I have to go through this line, so 9.55. Then I have a choice to go either through this line, 7.49, or I can go through both of these lines, which is 42.4 plus 21.2. So my parallel network, I have this option or this option. And then once I get there, I again have to go through this line, which is 2.12. So there's my overall resistance of 18.4. Then overall heat transfer, sigma times T to the fourth, the difference of those two factors for my two objects. First object's at 900 kelvins, second object's at 400 kelvins. So those 2 to the 4th power, subtract from each other, times sigma, 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the 4th power, divided by this total resistance of 18.4, gives me 1940 watts and then per meter, because again, these all resistances were per unit length, so 1940 watts per meter is the answer to that first part. Then the second part, I want to find my gas temperature. So to find the gas temperature, I basically need to know what this EB value is, EB for the gas. To do that, easiest thing to do is calculate J1 and J2. So to find J1 and J2, easiest way to do those is to find, I know what EB1 is, that's sigma T1 to the 4th power. I know this resistance, so I can find based on this resistance and those two values, I can set up this network Q, sigma T1 to the 4th minus J1 over that resistance, and then solve that guy for J1. So I get sigma T1 to the 4th minus 1 minus epsilon 1 over epsilon 1 A1 times Q, and those values I know. So 5.67 times 10 to the negative 8, sigma, 900 kelvins is this temperature, and then I know this resistance value was 9.55, and the total heat transfer being lost out this route was 1940. So with that, I get a J1 value of 18,674. That'll be watts per meter. Do the same thing for this line, this orange line over here, to find J2. So I know that the total heat, Q, which again is going to be 1940, is J2 minus sigma T2 to the 4th. Solve that guy for J2. Similarly, So sigma T2 to the fourth plus this resistance times Q. So 5.67 times 400 to the fourth power, plus the resistance over here was 2.12, and the heat transfer was 1940. Gives me 5,564 watts per meter for that guy. And then there's a couple ways I can do this. So the way I have it set up is kind of a complicated equation here, but what it came from is basically taking the current or heat. So I know this is 1940 here, I know there's 1940 here, but then that splits up into two different parts. So I don't know how much of this 1940 goes this way and how much the 1940 goes that way. But what I do know is that whatever comes this way has to also go that way. So basically this line and this line have to have the same value of Q. And so basically what I have for Q for this line here is J1 minus EB1. So that's my voltage essentially. And then the resistance for this guy is 1 over epsilon 1, epsilon gas, F1 gas. And so this, the total Q there will be this guy divided by that guy, but I just kind of rearranged it. And do the same thing for J1 minus J2. So what I'm taking now, instead of just taking this line, I'm taking this entire line from J1 to J2. And again, the heat in this entire line has to equal the heat in this line. So that's my second comparison. So this total distance or total voltage, total heat difference, J1 minus J2. Then this total resistance, I have both this guy, 1 over A1 EG F1G, plus this guy as my total resistance on the bottom. So again, I've kind of set up, here's my total heat, here's my total resistance. Q is this guy divided by this guy. But again, want to rearrange that, kind of move that to the other side. So I basically started with this guy over that guy equals this guy over this guy, and then just cross multiplied. So I can find the value of this because I know all these resistances. I know this total resistance is 42.4. This guy is the same as that guy, so 42.4. This guy is 21.2. So that total fraction is 2/3. So this fraction is 2/3. And now solving this equals 2/3 for EBG. I get that EBG is 1/3 J1 plus 2/3 J2. And then I know J1 is 18,674. I know J2 is 5,564. So EBG grand total 9,934. Once I know EB, I know that sigma times T to the fourth. So T is the fourth root of EB, 9,934 divided by sigma, 5.67 times 10 to the negative 8. Fourth root of that is 647 kelvins as my gas temperature. So that is the absorbing media part of this. Next up, we will have the reflecting media part of this, which is even more fun. So reflection, in one sense, is very similar to what we did before. However, in another sense, it gets a lot more complicated because there's a lot more going on. And so in general case, I could have transmission straight through the medium. I could have absorption and re-emission into the medium. I could also have reflection off of the medium. And so instead of having just alpha and tau, I now also have this reflection rho. So now my total energy either has to be absorbed, reflected, or transmitted. So I have this more general statement for my medium. And as usual, alpha and epsilon are the same thing. Diffuse radiosity, so total energy coming off of the surface. Jm is epsilon times EBM, so gas is at some temperature, or medium is at some temperature, sigma T to the fourth. Some of that is being emitted, of course, not necessarily all of it. And then I have some other energy hitting it, and some of that is being reflected. Total heat exchange, I have Q is area times E epsilon EB plus rho times G. And so that is EBM minus JM over 1 minus tau M divided by reflectivity rho over epsilon A and 1 minus tau. If I want to look at the specific example of a medium between two parallel surfaces like we had before, heat exchange between my two surfaces, same as before. So Q, J1 minus J2 over 1 over A1 F12 tau m. So this is the amount of energy that gets transmitted straight through the medium between surface 1 and 2. Unfortunately, that's not the only way you can get from surface 1 to 2. So now looking at the medium, the amount of heat leaving surface 1 going into the medium, J1 leaving surface 1, A1 F1m hitting the actual medium, 1 minus tau m is actually the part that hits the medium. Now some of this, unlike last class, this entirely stuff was absorbed last time. Now some of it will be reflected as well. Going the other way, energy leaving the medium arriving at surface 1, Jm, Am, Fm1. So this is the same as before. Net heat transfer, Q1m, J1 minus Jm over 1 minus tau m, over 1 over A1 F1m, 1 minus tau m. I can do the same thing for medium 2. So essentially just replace all these 1s with 2s, and that's what happens from medium 2. And now where things really get interesting is when we talk about reflection. There's 2 different types of reflection, specular and diffuse. So diffuse reflection, things kind of get reflected in all sorts of directions. So this kind of happens on concrete, for example, or any rough surface. Headlights on concrete, they get kind of spread out and basically just more diffuse. Is a good word for that, which is why it's called that. If you're reflecting off a smooth surface like a mirror, you're going to have specular reflection. So that means everything kind of reflects and you can kind of make out the same shape. So you can kind of still see the headlights, you can kind of still see the car. You can see a nice reflection in this puddle of water because that water is going to fill in all the imperfections in the concrete and make it a nice smooth surface. So a nice wet road, you see specular reflection, you can kind of see those headlights or the car, whatever it is much clearer. You can actually make out the fact that it's a car with headlights, as opposed to on concrete, it's just kind of a big blur. So some reflection is specular, some reflection is diffuse, and you can have both from the same object. So again, in general, both of them happen for any surface, so your total reflectivity is a combination of the specular and diffuse portions of it. Everything we did up to now, we assumed was purely diffuse reflection, so things kind of get reflected in all sorts of directions. So obviously, as you can imagine, this is very complicated. It was already complicated enough without this added complication of 2 different types of reflection. So really complicated scenario. Basically, all we're going to do is do a quick example to finish this off. So here we go. Have 2 parallel discs, 10 centimeters in diameter each, both separated by a distance of 2.5 centimeters. One disc at 625 Celsius. This guy's completely diffuse reflecting, has an emissivity of 0.25. Other disc is at 250, has both specular and diffuse types of reflection. Diffuse is 0.2, specular is 0.4. Surroundings maintained at 20 degrees Celsius. Want to calculate the heat lost by the inside surface of each disc. So radiation network for this guy, similar to what we had before. I have my surroundings, EV3 really large, and so its own node down here. I have object 1, again with this normal resistance to get off the surface of 1 minus epsilon 1 over epsilon 1 A1 for the diffuse reflector. Object 2 is a bit more complicated because it's diffuse and specular reflector. So to get off its surface, I have rho 2d divided by epsilon 2 A2, 1 minus rho 2s. So this is the reflecting part of it coming off. And then between the two, I have 1 over A1 F12, 1 minus rho 2s. So again, that's the specular part of it. And then going into my gas, from object 1, I have A1 F13. So that's basically what comes straight to from 1 to 3 straight there. I can also get from 1 to 3 by reflecting off of object 2. So I have some reflection, rho 2s, off of object 2. So basically that's why I have 2 in parentheses down here. So I have some shape factor that goes from object 1 to object 2, and then reflected off object 2 to object 3. So that's what this subscript down here means. It's kind of like if I'm holding a mirror, can I see myself in the mirror? And that's kind of what F123 is. And then going from the gas to my object 2, I have 1 over A2 F23, 1 minus rho 2s. So again, object 1 being diffuse reflector, I don't have any stuff coming off of him hitting object 2 because it's diffuse reflection. It's going off in all directions. So it's only the specular part that actually have to worry about reflecting off things to get to other places. Again, all the stuff we know from the question. More calculations that we're going to need to do. So EB1 is sigma T1 to the 4th. So temperature 1 was 625 Celsius. Convert that into Kelvin to the 4th power. 5.67 times 10 to the negative 8 sigma gives me 36,871 watts per square meter for object 1. Similarly, disk number 2, he was at 200 Celsius, I hope. 250, that's not good. So that should be 523, so I'll have to change that later. Gives me EB of 4,242, and then EB3 is 418. Again, doing the same thing, the surroundings are at 20 degrees, so 293 to the 4th power times 5.67 10 to the negative 8. That's what that comes from. So again, temperature 20 degrees, convert to Kelvin, 4th power times 5.67 gives me this value here. The area of the two disks, pi r squared. They both have 10 centimeter diameters, so pi times 0.05 squared gives me that area. And then the absorptivity and reflectivity equals 1. So my emissivity is 1 minus rho. Also know that rho is rho s plus rho d. So for object number 2, nothing's transmitted through the disks. So that's why I don't have transmissivity here. So for object 2, 1 minus rho 2 gives me its emissivity. And again, the total rho is the total diffuse and specular parts. And then F12, the shape factor, I need to find between the two disks. So that is just using the equation for the view factors, 0.61. And then whatever does not make it to the two disks makes it to the surroundings. So the surroundings, F13 is 0.39. So that'll be for both of them from F13 and F23. And then I need to calculate this reflection. So basically what happens with reflection is I need to go from object 1 to object 2. So I need F12. Then I need to go from object 2 to object 3. So that's F23. So those two guys multiplied together gives me this reflection view factor, F123. So that's 0.238. And then I can get all my resistances. Again, plug in all my values for all my epsilons and areas and rhos, rho s's, rho d's, areas, f's. So let's plug them in to where they belong. So 1 minus epsilon 1 over epsilon 1 A1. This resistance here, 382. Rho 2d over epsilon 2 A2 minus rho 2s, 106. That's this guy over here. This resistance was for the top up here, 348. And then this guy was over here, 544. And then this guy with the reflection down here is 263. Now again, I can look at my two nodes and do an energy balance. So this node right here, I have EB1 minus J1 coming in. So EB1 minus J1 over 382 equals whatever goes out. Going out, I have J2 minus J1 over 348. That's one option. I also have J1 minus EB3 over 263. That's my second option. So here's equation number 1 essentially for J1 and J2. I know my EBs, and so the only unknowns in this equation are J1 and J2. Do the same thing for this node. So EB2 minus J2 over 106. Call that going in or going out, doesn't really matter. Equals the other things. J2 minus J1 over 348 as option number 1. Or J2 minus EB3 over 544 is option number 2. And so again, here I know my EBs. Only two things I don't know are J1 and J2. So basically I have two equations for two unknowns, J1 and J2. I can solve those. J1 is 12,000 roughly watts per square meter. J2 is 5,300. watts per square meter. And then I can find my Qs, because I know just based on these orange lines, Q1, EB1 minus J1 over 382. EB1 was 36,000 minus J1 of 12,000 over 382 is 64.5 watts. Same thing for this line here. Q2, EB2 minus J2 over 106 is 42 minus 5365 over 106 is negative 10.6 watts. So the way I've oriented all of these EBs and Js is so that energy is flowing out of them. So energy flowing out is energy lost. So this 64.5 watts is actually energy lost, which is what the question was asking for. This minus 10.6 watts means negative energy being lost, means I'm actually gaining, or object 2 is absorbing 10.6 watts of energy. If you remember, object number 1 was at the higher temperature. Object 2 was at kind of the medium temperature. The surroundings are the lower temperature. And so obviously object 1 is going to lose energy. Object 2 is kind of iffy whether it loses energy or gains energy, because it depends on how much energy is coming in from object 1 and how much energy it's losing to the surroundings. So we can see that it's actually gaining a bit more energy. So it's actually gaining 10.6 watts. So that is reflection. That is the hardest part of radiation. As you can see, it actually gets very complicated. And so for that reason, you probably don't have any or very many homework, if you have any homework problems on it. If you do have any homework problems on it, it'll be very similar to what we just did. Won't be any exam questions on it because, as you can see, it gets very complicated. So up to where we stopped for absorption is kind of where your exam 3 is going to end. Next class, all we have is a numerical way to do things. So that will make things a little easier. So basically to finish off homework 5 will be the topic of next class. So hopefully you've started homework 5, like I mentioned about a month ago, and did those conduction questions. Next class we'll deal with the radiation part, the last question for that.